Good morning, everyone. Welcome to the latest series of Future of Technology. Today, or over the next 4 days, we'll be running events around hydrogen, looking at some of the challenges and opportunities, both within the UK and internationally, around both the supply, distribution, and of course, the consumer and end use of the technology. Today is day one, where we were looking at the road to green hydrogen. We will be setting the scene with a current overview of technology development and hydrogen production and addressing the global and UK ecosystem, as well as ending up looking at some of the opportunities around the automotive sector itself. I'm joined by 4 fantastic speakers today. Dr. Sam French, Business Development Director for Johnson Matthey, Claire Jackson, who's a Senior Consultant at Ecuity, Professor Nigel Brandon, who's the Director of Hydrogen Fuel Cell Research Hub, H2FC Supergen, and last but not least, Ralph Clegg, who's Head of Hydrogen and Fuel Cells at Jaguar Land Rover.
Thank you very much for the opportunity to speak this morning. Want to cover a bit of around hydrogen's implications, where we see hydrogen playing a key role in the energy transition, and I suppose try and touch on some of the key points that need to be addressed to really make hydrogen happen at scale. So very quickly, for those who don't know, Johnson Matthey is a FTSE 100 company based in the UK, just over 15,000 people globally. Just over 200 years old. One key element is we're very technically focused, so our real underlying for all of the different markets we're involved in is sustainable technologies, and we really invest heavily in R&D and look for the key elements of chemistry, catalysis, and other people's processes where we can help and support. Hydrogen has many such areas, and we'll try and cover some of those as we go through this presentation. So first of all, why are people talking more and more about hydrogen? Well, I think one of the critical changes has been this desire or targets and ambition to achieve net zero. The change from an 80% emissions reduction to net zero has really highlighted areas of our energy system which are hard to abate, and these are the critical areas where hydrogen can really play a key role, and we'll try and describe some of those as we go through the presentation. You'll all have seen, and this is probably slightly out of date now, being December 2020, the way things are moving in this arena. It's only accelerating, but more and more countries are now backing net zero, defining their own targets, and actually legislating. What this is really doing is highlighting the fact that the large amounts of GDP are associated with achieving those net zero targets. COVID has happened, is still happening globally, but what we're really seeing is that's not slowing down this trend. It may have distracted people, and I think that's an important part that we may pick up later on. The fact that what is critical for us to achieve net zero is for us to be starting now, to be deploying at scale, not waiting, not seeing that this is a problem that we can come back to, really needing to drive action today. Whilst we're talking about hydrogen, we have to put it in context of a global energy system. What we'll have seen, and you'll have seen recent headlines around the fact that we've had more renewables, particularly in the UK, contributing to our energy system than ever before, actually heading towards a tipping point where more renewables are being used than fossil fuels. But mainly this is for electricity, or nearly all of this is aimed at electricity generation. And that's absolutely right. What we're not here to do is say hydrogen's the only solution. Hydrogen is one of the solutions that will help us get to net zero. Actually, the electrification is going to be critical, and how hydrogen interfaces with that electrification or by renewables will be key. So we very much see that there are real markets, large markets for light duty transport, most rail applications on main lines, some heatings in homes and light industrial processes where electrification will be critical. We've got to remember we're moving from a global energy system that today has about 80% energy coming from molecules, whether that's fossil fuels as coal, oil and gas, versus 20% from electricity. So the growth in our electricity system is going to have to be massive. Where we see hydrogen, and we'll come into the different routes of getting to hydrogen, are in the energy intensive industrial uses. So these are primarily things, cement, steel manufacture, but also a lot of high temperature processes used in industry, which will really struggle in the near to medium term to shift to electrification. Heavy duty transportation, marine, and some rail applications, particularly branch line type applications, we also see as really critical areas, these hard to abate sectors where hydrogen will play a key role. Also, we certainly see examples coming through globally of where larger and longer range light duty transport will also benefit greatly from a shift to hydrogen. Aviation's on there. I will have to wait and see whether we'll ever be flying a jumbo powered by hydrogen, but there are many other applications within aviation where hydrogen will certainly be a key enabler to decarbonising that sector. And equally, we're going to start seeing areas where we're going to get crossover between renewables, hydrogen, and then potentially onto things like sustainable aviation fuels. That's shown a little bit here in this, this flow diagram, where there is the potential that we can move from to a system where we're using renewables and water to generate hydrogen through electrolyzers. We can pull CO2 either from waste sources, from industry, or from, for example, the use of biomass to create power. We can then upgrade that to hydrocarbons by a variety of different routes. Many of these are technologies that Johnson Matthey is actively engaged in, either by providing components or full technology processes, where we can then get to fuels, chemicals, fertilizers, all to drive a more sustainable and greener future. Now, this is a technology-driven map at the moment. We know how to do these blocks. What we don't have in place is the market conditions to make many of these things happen. Particularly when we're looking at things like the ammonia and methanol market. These are global commodity traded chemicals. We will need a global market or a differentiated market to drive low carbon equivalents or low carbon options. And we will have to be looking at how we deal with that global trade. Other elements such as sustainable aviation fuels, which will be driven through things like upgrading via Fischer-Tropsch synthesis, where we take potentially CO2 and hydrogen through to jet fuel or kerosene. That can be more of a localized market within a country. But we are going to have to think about how we enable these new routes to compete with the current routes via fossil fuels. Back to hydrogen. You're probably all aware of the rainbow that comes with hydrogen, and I'm only showing 4 of the different colors that are often mentioned. A brown hydrogen coming from coal, very high emissions, but you can see is a very low cost per kilogram of hydrogen, and that's the competition we're in. Most hydrogen today is produced by steam reforming of natural gas, or grey hydrogen. This is a segment where Johnson Matthey supplies catalysts globally. Again, a high emissions per ton of hydrogen, but again, a very competitively priced product. And this is what we're having to compete with. When we move to blue hydrogen, where we again use natural gas, but now use carbon capture and storage, we can dramatically cut those emissions. Johnson Matthey developed a technology called LCH, where we use key part of that is that we use differentiated technology to drive down the overall emissions by making it as easy as possible to capture the CO2 from the process as cost effectively as possible. And we can achieve over 95% CO2 capture, in some cases up to 98%. This again is a relatively low cost process, but is more expensive than today's grey hydrogen. So we do need to work on ways to make that transition happen, whether that comes from a carrot and stick model, where there's subsidies for blue hydrogen and the stick being more like a carbon price, which then reduces the amount of grey hydrogen that's produced. We will need these market mechanisms to enable this. And I think that's one of the take homes that I'd like people to go away with, is that it's not about the technology, it's about the market and how we stimulate this change in behavior. Finally, green hydrogen. Really what we're talking about here is water electrolysis, either from alkaline electrolyzers or polymer electrolyte membrane electrolyzers. This has the potential to be a zero emission technology if we are using 100% renewable electricity to generate hydrogen. Currently, the prices are high, but that's as much as anything due to electricity prices still being relatively high as a key feedstock, and also the relatively small size of the supply chain, which will have to grow to meet some of the aspirations. What could hydrogen do in the future? These are numbers that we've pulled from some work from the Hydrogen Council and IEA. Maybe focus less on the split between blue and green hydrogen. We can argue about that probably till the cows come home. The key thing here is we're seeing a dramatic growth in hydrogen between today and 2050. This is shown in terawatt hours. Grey hydrogen today, still a substantial amount of hydrogen is made. The emissions from that are equivalent to the total emissions from the UK and Indonesia combined. So not insubstantial. And we will have to see that phase out over the decades. This will happen as current existing assets go out of action, come to the end of life, and we'll start seeing the growth of blue and green hydrogen. And really you can see that we're looking minimum a 10-fold increase in the volumes of hydrogen required. So grey hydrogen is going to decline due to future carbon prices. We think blue hydrogen will be picked up and adopted in areas that have good geology to allow carbon storage to happen cost effectively, but also areas which have a strong infrastructure for natural gas and distribution of natural gas. Those are areas which will really suit blue hydrogen. UK being one example, but equally the US and Canada, which have a large access to low-cost shale gas. We don't see this being a question of blue or green. It's blue and green. You can see the amount of hydrogen we need there is, phenomenal in terms of change over 30 years. So it's not about one or the other. And actually, there are a lot of synergies between blue and green hydrogen. Certainly, we're seeing a lot of interest in green hydrogen in areas which have very low cost renewables. You can see this being places like Chile, which have a lot of solar and particularly wind. Areas such as the Middle East, where there is equally a lot of low cost solar. But the same here in the UK. Up in Scotland, we have the ability to tap a really large offshore wind resource, and green hydrogen could well be a way of driving that. Because remember, we've got to move from an energy system with 80% molecules and 20% electrons. We're going to have more and more renewable electricity, more electrons in the game. But to have a stable energy system, we need something that's balanced, that we can store. And this is one of the key elements that hydrogen can bring to a balanced energy system. Costs, and we mentioned briefly costs before. What we see is that essentially blue hydrogen will be one of the more cost-effective routes for a number of years, particularly in locations like the UK. But we do anticipate a large cost down in green hydrogen, and in some areas it will become more cost-effective to produce green hydrogen over time than blue hydrogen, with grey hydrogen becoming ever more expensive as carbon prices rise. So what's happening? Well, that's, you've already mentioned, Philippa mentioned in the introduction, the amount of news, discussion, talk around hydrogen is growing, ever growing. What this is showing is some of the commitments made by governments in terms of targets they're setting over different timeframes, some in different sectors, whether they're stimulating supply or demand. But really the underlying message is this is a global thing. We're seeing more and more countries engaging in looking at hydrogen and really looking at hydrogen at scale. And the key there is that will then increase the supply chain and drive down costs. However, it's no point just looking at what governments are targeting and the ambitions they have. We also need to really consider projects. What this is showing is that there are a large number of projects that have been announced globally. And also there's a difference in where these different countries, different regions are targeting that within the supply chain. So it's not all just about production. It's how you produce hydrogen and then how you transport, store and distribute it. And then the multiple end uses that you can really take up that hydrogen. Different countries have different strategies and are focused on different areas of their energy, of their economy, different sectors. However, it's relatively easy to announce projects, and here you'll see that there is many more projects that have been announced. But I think what's key is that we're also seeing these announcements transitioning from that very early stage, now moving into planning and post-investment decision. Critically, their final investment decisions, where people are now starting to really construct, commission and operate these projects. And that's accelerated rapidly over the last few years. Back to the UK, I do think the UK has a real opportunity to be a world leader. We are very positive about things like the announcements made through government in the 10-point plan at the back end of last year, where hydrogen was very prominent. We also see the requirement for growth in renewables to drive green hydrogen and the importance of carbon capture and storage for blue hydrogen. All of these are real telltale signals from government that they are absolutely going to push this forward. We are waiting for the hydrogen strategy that should be due out in the next couple of months. And these have really quite ambitious targets. Maybe some of the other speakers will challenge whether they are ambitious enough. But to be looking at 5 gigawatts of hydrogen by 2030 as a minimum is a really good starting point. I think key to what the UK has done and UK government has done is they pushed funding at an early stage into some key projects around the UK that can really be world leading. So 2 projects that I'm mentioning here, HyNet up in the northwest of England. This is everyone likes different units, but 80,000 tons per annum of hydrogen, or 350 megawatts equivalent. This is a large blue hydrogen project, which is you're going to use Johnson Matthey technology at its core. Particularly relevant here is that that's going to be used in industry in the first phase. But what we really see is that the clusters will start building. And once we have these clusters of large volumes of hydrogen being produced, we'll see spillover into other sectors. So while industry might be the first starting point, as subsequent phases come online, we'd equally anticipate that being blended into the gas grid and used in transportation. Another project up in the northeast of England this time is the Gigastack project. This is using electrolyzers, specifically again electrolyzers coming from a UK company called ITM. So really seeing that we have two world-leading projects that are really pushing UK technology and UK content to the fore. This project up at 100 megawatts would be the largest electrolyzer installation in the world, using offshore wind from the Hornsea 2 wind farm out in, and this is one of the many projects that focused on decarbonizing the industrial sector around the Humber. A lot of the hydrogen will go into the refinery, some of it likely to be replacing existing uses of grey hydrogen. So I think summary of that is that the UK does have an amazing opportunity to be a world leader. Really for us to drive a legacy into the UK, particularly into the supply chain, and that's all elements, it's services, it's engineering, it's manufacturing. We need to be one of the first and not to be a follower. If we're a follower, we'll end up importing key elements of the supply chain. So I think this is one of those timings where we've done a lot of good work. We've made some really impressive start, but we've got to follow that through, and we've got to deploy these projects at scale. The really critical next step, hydrogen strategy, is part of it, but it's the business models that are going to allow these projects to go ahead, which are really going to define the position we can take in the UK. Very quickly then, just heading towards wrapping up. There is a lot of interest in fuel cell electric vehicles, and these do run across multiple sectors. One of the elements that everyone always talks about is the infrastructure, so the hydrogen fueling stations. We are seeing more and more plans and strategies coming along from multiple governments that are looking to install these. We need a similar element within the UK. This will then drive both the uptake of light vehicles and heavy vehicles. And it will be, once we have the infrastructure in place, we will be able to see the uptake of fuel cell vehicles in multiple sectors, heavy duty vehicles being one where we see a real need for that deployment. Oh, and then finally, I think you'll all seen kind of pictures like this. One of the key elements is the power that hydrogen brings you, is that when you start bringing it into these clusters, it has multiple different uses. We can export it by ship, by pipeline. We can be using it for shipping. We can be using it to produce synthetic fuels for aviation, clean mobility, replacing existing grey hydrogen in commodity products such as ammonia and methanol, reducing emissions from refineries, and also producing products such as green steel, low carbon glass, and other industrial processes. So we do see that these clusters will be critical to the beginnings for hydrogen, but these will then spill out, particularly in regions and areas which have a good existing gas grid, as we do here in the UK. So with that, Philippa, I will close and happy to take any questions.
Yeah, great. Thanks, Sam. I've got a quick question myself to start off with. You talked about the focus needing to move to deployment and that needed to be prioritised. Do you think that the projects like HyNet that you discussed are good enough to accelerate this market uptake in terms of the deployment factor, or does more need to be done? And should we be prioritising particular areas?
There's a few questions in there.
Sorry.
So HyNet's one example. There are great projects up at Acorn in Scotland, at St Fergus. The projects announced by Equinor and the Humber and now BP in Teesside. We'll need all of these. Along with multiple large-scale electrolyzer projects. We need to start somewhere though. So getting some of them over the line as quickly as possible is important, with the view to then being ready to deploy at scale through the 2030s. So it's certainly not just about doing a couple of projects and then sitting on our laurels. It's really about developing a pipeline. Key to that will be getting the business models over the line. Likely that there'll be individual negotiations for the first projects, but then we could well see ourselves in a position similar to offshore wind, where we've got kind of CFD type auctions happening at set periods during the 2030s.
Right. Right, quite a few questions actually coming in towards last day. So first of all, we're going to go to Mark Sanford, who I believe is going to ask his question live.
Yeah, is that working?
Yeah, I can hear you, Mark.
Yeah, so I'm particularly interested in the relationship between the green and blue hydrogen. And I was wondering if you had a rough idea or prediction for when essentially green hydrogen could overtake the production of blue hydrogen in the UK, and if you think there's any tipping points that green hydrogen could overtake blue, for example.
It's my fault in terms of introducing the rainbows of hydrogen. I'd really prefer if we talked about low carbon hydrogen and actually got into some of the sort of life cycle analysis for these different routes. But on your question, there will be examples where the cost of green hydrogen will become lower than blue hydrogen in areas which are further away from the clusters, where you have to start paying for transport and potentially storage, and actually producing locally will be cheaper. Driving down the cost of renewables in certain areas will also make that happen. As well as I think there's some technical advances required in green hydrogen, but the main thing will be driving up the supply chain volumes, which will drive cost out of the capital. I can't give you an answer of when the tipping point would be. I think some of that will come down to what government do in terms of whether electrolyzers can access wholesale electricity prices, whether grid connection fees are waived, VAT, all sorts of complicated elements to their business model. Key for me is I think we need both, and I think we need large volumes of both. So I'd be less about one or the other, but more about driving and making sure both have support particularly as they fit well with different parts of our energy system. Now, high temperature, large baseload requirements through industry probably fit much better with a blue hydrogen approach, whereas a more distributed network of hydrogen fueling stations, as well as areas that are far away from carbon capture and storage, we should be driving the use of green hydrogen.
Do you have any sort of ideas around those sort of prices that will be needed?
Hydrogen pricing is quite difficult actually, because today, there isn't really a hydrogen market. Most grey hydrogen's produced and captively used, so over the fence with direct contracts. What I think we'll see in the near term and this is work that BEIS are doing at the moment around business models, is that the production side will be subsidized, and therefore the consumer will pay, large industry consumers will pay about the same price as natural gas. Now, over time, that subsidy will drop off as the cost of production comes down and the cost of gas rises via a carbon price. So I don't think I'm talking out of turn, but I think that's the favored model from government for at least large scale production. For smaller scale production, primarily from green hydrogen, it's likely a different business model will be invoked. And there probably you're also targeting higher value market opportunities such as transportation fuel, which on the whole can carry a higher price. But there are mechanisms such as the renewable transport fuel obligation, which if done correctly, would provide a sufficient subsidy to make the business models work for green hydrogen. So it's not a simple answer. There are different models for different industries, but large scale industry, you could even think that that could extend to domestic heating. You would look at mapping to a reference price of natural gas.
My name is Claire Jackson. I'm a senior consultant at Ecuity, and we make up half of the sort of secretariat of the Hydrogen Task Force. So just to give you a little bit of an introduction as to who the Hydrogen Task Force are. So we are a sort of group of organisations that we sort of launched March last year. So we bring together the organisations that are leading or looking to lead on hydrogen in the UK across the whole sort of value chain. And we're looking to sort of develop a vision for hydrogen in the UK, so what could be achieved here, and then sort of develop a sort of collective position on the next steps that need to happen now to make that sort of vision a reality. So part of that is looking to make that sort of high level sort of energy system, economic, environmental case for why hydrogen is really important in the UK. And we have around sort of 20 organisations that are involved in this process. You might sort of notice there that we don't have an awful lot of companies that are working in the sort of end use areas of the transport sector. So really interested if there are any sort of organisations that are watching today who are interested in being part of this process. We'd really sort of value that expertise. In terms of why hydrogen, Sam's touched on a little bit of this, but I'll just sort of talk about it as well. So we sort of see there's a number of reasons why hydrogen is really important for the UK. Our view is that, whilst hydrogen is not a silver bullet, it can't solve all of our problems. It's not going to get us to net zero on its own. That actually net zero is actually not possible without hydrogen. Hydrogen has a really key role to play, and that's for a number of different reasons. A number of different sort of benefits that hydrogen has. So first, it enables us to sort of have a greater deployment of renewable technologies. So we're sort of starting to get to a point now where, as we're deploying more offshore wind, we're starting to get to a point where we're actually experiencing some curtailment. Times when demand is low, but the wind is blowing and it's all sunny, and we're starting to sort of switch off some of those renewables, which sort of impacts the economics of those technologies. So by having hydrogen as a potential storage mechanism for some of that, we can start to deploy even more of those renewables over the next decade. Hydrogen also, the use of hydrogen will also reduce pressure on the electricity transmission networks. So that's as opposed to a sort of complete electrification of everything that we can sort of electrify. So just to sort of give you some sort of context for that. So we have around sort of 350 sort of terawatt hours of electricity sort of demand in the UK annually. We also have about 750 terawatt hours of heat and about 650 terawatt hours of transport, which all use sort of chemical energy carriers. So if we were trying to move those two domains onto the electricity transmission network and electrify them all, we're sort of talking about sort of 4 times as much cables that we would need to lay. And you all experience that disruption that happens when we start digging up the roads to try and reinforce our electricity transmission network. So perhaps using some of the sort of existing infrastructure that we've got in terms of the gas network could be a really great way of reducing the pressure that comes from electrification on the electricity transmission network. And sort of part of that is around sort of demand variation and storage. So, for example, heat has a really big sort of seasonal swing, and being able to store energy in the summer and use it in the winter, using something like hydrogen would be really beneficial. Hard to abate sectors that are really hard to electrify, such as sort of industrial applications, some of those heavy duty sort of transport applications. Hydrogen is a really good fit for that. Sort of energy system resilience, not just being reliant on one thing, but also having that sort of slightly more rounded energy system. And also then there's the global market opportunity. So hydrogen, as sort of Sam outlined there, getting an awful lot of attention globally. There's going to be a big demand for it globally, and if the UK can come out ahead of that, then there's a huge potential benefit for the UK in that. So some key questions, I think, for sort of 2021, the sort of things that we're thinking about now is, what is the role of hydrogen in the UK? What role could hydrogen play? And what do we actually need to do now in order to achieve that? So some of those questions, so how much hydrogen, realistically can we produce? If we have this hydrogen, where should it be used? Which parts of our energy system? What are the sort of carbon implications for using hydrogen? What are the energy system implications for using hydrogen? Where is it that the UK can take a sort of global leadership position? Where should we be a leader and where should we be a follower? What are the existing assets that we have that we can leverage? And what sort of economic benefit would this unlock if we were to do this? And then the question of, what is it that we need to do now in order to sort of unlock that? What are the barriers? Why is this not happening now? What business models do we need to have in place in order to start to scale these technologies? What's the role of government? What's the role of industry? How do we encourage coordination across the different sort of sectors? Hydrogen is not a sort of single technology. It's a whole sort of ecosystem. With all of these different end use technologies, if we're starting to look at clusters, how do we get sort of coordination there? How do we ensure that we've got the right skills as we scale up? What infrastructure might we need? And also, how do we ensure that we're bringing consumers along with us in this? A lot of these technologies are going to they're going to touch the end consumer, whether that's hydrogen boilers in your house or whether that's sitting in a hydrogen fuel cell bus on the way to work. And we need to make sure that we take consumers along with us. So I don't have time. I've got 10 minutes to go into all of these questions. But I'm just going to sort of touch on a couple based on some analysis that the Hydrogen Task Force has done recently around sort of what might we be able to achieve in the next 10 years in terms of hydrogen production, and where in the sort of end use sector should we be putting that hydrogen. So this is the world's most boring slide in the sense that it's a table with a bunch of figures on it, but I've got a graphical format of it on the next slide, but I think having the figures on the pages actually can be really helpful. So the 10-point plan, as Sam said, the government's committed to trying to reach a sort of 5 gigawatt production capacity by 2030. So we've done a bit of an exercise over the last few months of looking at all the different projects that are in the UK that are currently in the sort of pipeline of things that people have started to put plans together to do, like HyNet or Acorn or the sort of Teesside project. And we basically aggregated all of those. And that's sort of our high scenario there. Is an aggregation of all the projects that everyone wants to do in the UK at the moment. So that sort of totals up to just under 23 gigawatts of capacity, with a sort of demand of servicing a demand of 160, just under 162 terawatt hours of end use demand. And what we've also done is looked at those projects and looked at where those projects want to put the hydrogen. So where are they saying that they're going to sort of put hydrogen at the moment? And that's where you see the sort of those figures there. We've also then done a sort of central and low scenario. So the Hydrogen Task Force members have given us some sort of views on where the constraints might be. which sort of end use sectors might be able to move a little bit quicker, where there's a little bit more uncertainty. And so we sort of pared down those for sort of low and central scenarios. But I guess a couple of things to note on this is firstly that there's an awful lot more in the pipeline than what the government says that it wants to do by 2030. That's not to say that we'll be able to do 23 gigawatts by 2030. I think that's wishful thinking. But we might be able to be a little bit more ambitious than we're being at the moment. I'm just going to sort of flick onto the next slide, which is a sort of slightly more graphical form of those sort of three scenarios. I think what you sort of note here is that the sort of big sort of sectors that are going to be taking that hydrogen in the first instance are sort of industrial applications, potential sort of power generation, and also some blending within the sort of gas grid. And you'll see that actually, we're talking about transport, but the actual volume of hydrogen that would potentially be used in transport is actually low. And I guess the thing that I would say about that is that's not actually necessarily reflective of the sort of number of, we can still get some pretty decent numbers of vehicles on the road. They don't actually necessarily need a huge amount of hydrogen. So if I just sort of, flick back onto this screen, if we're looking at perhaps 100 terawatt hours of hydrogen by 2030. So if so 1 million cars is about 3 terawatt hours of hydrogen. Similarly, if we're looking at 10,000 buses, that would be sort of 2 terawatt hours, or 10,000 HGVs, they use about the same annually. It's about 2 terawatt hours of hydrogen. Or 1,000 trains is 1 terawatt hour. So that we can get some reasonable volumes of vehicles. They don't necessarily take as much hydrogen. So although that little red slither looks quite small, it's actually reflective of some reasonable numbers of vehicles. So the other thing the Hydrogen Task Force did last year is we looked at a sort of economic impact assessment. We think that there's significant value to be gained from the UK not being a follower, but being a sort of leader in hydrogen technology with this huge export potential. So we've just basically looked at the economic value and job creation on a sort of 2035 timeframe across the sort of hydrogen value chain that could be created or protected in the UK by sort of pursuing hydrogen. And we sort of estimate that we could see 18 billion of GVA and 75,000 jobs by 2035. And again, just sort of picking out the sort of transport numbers there, we can see about 1.7 billion of GVA and 9,000 jobs in the sort of transport sector. So we think there's sort of huge value to be gained by moving quickly in this area for hydrogen. So in terms of sort of next steps and what needs to happen now, sort of Sam has again sort of touched on this. There's a number of things that need to happen sort of over the next 10 years, but I think particularly looking at what needs to happen now, we are going to see a hydrogen strategy, which is we're very excited about seeing that in the next sort of couple of months. This sort of comes alongside, what's happened sort of globally. We've seen lots and lots of countries coming out with targets and strategies, and the UK will be next. It'll be really important that this hydrogen strategy is ambitious and sort of sets us up. And then the second thing is the sort of business models. This is absolutely critical for getting these early stage projects off the ground. And I think it's important in this area that the perfect doesn't become the enemy of the good. And I think getting those early stage projects off the ground will be really key for the next year. So that's all that I'm going to sort of share, and I think I'll pass back to Philippa, who I think will introduce the next panelist.
It's a pleasure to be here. So yes, I'm Nigel Brannan. I'm head of the Hydrogen and Fuel Cell Supergen Hub, which is funded by the Research Councils. It's an academic led hub, but has a whole body of industrial partners and advisors, including folk like Sam and Ralph. So it's a pleasure to be here. We also have our Sustainable Gas Institute at Imperial College, which is looking at all issues around gas and its sustainability. That includes natural gas and hydrogen and biogas. And I'll give some web links at the end if people want to go and look at a bit more detail. Just a couple of opening comments, and this is reflective of some of the numbers you've already seen, but I think it's a very helpful way of looking at the energy flows that we have in the UK. It comes from my colleague Grant Wilson at the University of Birmingham, and I'm grateful for Grant for providing it. And it reminds us that we have the red squiggly line at the bottom there is the flow of energy as electricity. The horizontal line is the flow of energy as liquid fossil fuels, that's gasoline and diesel primarily for the transport sector, and the blue line with this big seasonal variation is the flow as natural gas. And it's transitioning across all of this that, of course, is the challenge for us for net zero, and it picks up on the points that Sam and others have made, right, which is how do you decarbonize? It really gets extremely difficult and expensive to decarbonize all of that energy flow with electricity alone, and that having some energy flowing as low carbon molecules like hydrogen, or indeed other low carbon carriers like green ammonia, may give us a whole bunch, gives us the lowest overall cost to energy decarbonisation, and that's what really matters. So this kind of purist debate about whether it should all be electrons or molecules is not terribly helpful. It actually will need both. And whilst we're focusing on carbon, particularly in terms of the air quality issues in cities and the transport implications of that, this is a little bit old now, but it shows you a NOx map of London with high NOx levels breaching EU regulations around the main arterial roads through London. So it's clearly a fact that we need to think not only about carbon but air quality, and hydrogen has a role to play with that, particularly if it's used as a transport fuel and converted through a fuel cell. There was a question, I think, in the chat about, which kind of implied we might burn hydrogen, and I don't think we will. Form of combustion engine, not on a road vehicle anyway. And that's not to say we might not consider it in gas turbines for power generation, or possibly even for ships, but I don't see it for road transport. I think it's a fuel cell conversion. And this is my picture of a similar picture you've seen before, showing that hydrogen is really an enabler for an energy system, so we don't need to look at that anymore. In terms of the costs of hydrogen, and I can understand why, you know, it can be a difficult conversation about green hydrogen and blue hydrogen. I'm an electrochemical engineer. I mainly work on the electrochemical technologies. I just want to reinforce Sam's view that we need both blue hydrogen and green hydrogen. We need all the low carbon hydrogen we can get. And today, the most expensive form of hydrogen is green. Green hydrogen is a lot more expensive than blue, and blue is more expensive than unabated hydrogen, which of course you would expect, because unabated hydrogen, we haven't got to go through the carbon capture step. But if we start to look at the prospects for cost down on green hydrogen, this comes from a report from IRENA. It's quite a useful report if you want to go, and it's publicly available. I had nothing to do with the report, but it takes a fairly rosy-eyed view of where costs may come down. But I guess the key point to take from it is that somewhere between 60 and 80% of the cost of green hydrogen, so hydrogen from electrolysis powered by renewables, is the cost of the renewable electricity. So the biggest driver here, in terms of the question that was asked about the tipping point of green versus blue, is the cost of the renewable electricity. And all of the price assumptions or future cost assumptions around green hydrogen are really very sensitive to that. And therefore it will vary depending where you are in the world and the price of renewable electricity. There are certainly some commentators who would say that once you get down to around $30 a megawatt hour, then your green hydrogen should be cheaper than blue. But as Sam has pointed out, actually it's quite a bit more complicated than that, and depends on many other factors as well. But suffice it to say, as we continue to see the falling price of renewable electricity and we continue to see innovations in the electrolyzers themselves, that should help drive down costs. But green has a journey to go on before it's cost competitive with blue hydrogen. So I just wanted to kind of spend the rest of my talk talking about where things are today in terms of the transport piece. And we're followed by Ralph, who I'm sure will give us a much more detailed view of the work he's and his colleagues are involved in at Jaguar Land Rover on this, but the kind of a broader perspective of where hydrogen fuel cell technologies are for transport applications. And it's really that integration of hydrogen as the energy carrier on the vehicle and the fuel cell as the highly efficient energy conversion device that takes that fuel and turns it into electricity to then produce an electric vehicle that we're talking about. And of course, Toyota have been leading in this space for a long time. This is the Toyota Mirai that we have at Imperial College London. And they are available in small numbers in the UK. Toyota have brought out a more recent version of this, and of course Hyundai have their Nexo as well. These remain relatively expensive vehicles to buy, but in terms of an electric vehicle that can drive a good range of 300 to 400 miles, and you can refuel in a few minutes, using, by the way, at a Shell forecourt, an ITM electrolyzer, which is the same type of electrolyzer that Sam referenced in that very large-scale project that's happening in the UK. So that's really where I'm sure cars are, and we'll hear more from Ralph, I'm sure. As previous speakers have alluded, both Sam and Claire, I think the big opportunity in transport is also in heavier duty vehicles where the energy requirements are higher and there's a less obvious, you're competing less obviously head to head with battery electric vehicles. The Optare bus at the top there is a collaboration between Arcola Energy, or a UK-based fuel cell integrator, and Optare, which is this hydrogen fuel cell double-decker bus manufacturer in the UK. You've got Wrightbus as well, very active in this space in Ireland. And of course, we've had those RV1 fuel cell buses as part of an EU program running in London for a long time. But there are big programs globally around hydrogen fuel cell electric buses. I think a rapidly emerging area is around hydrogen fuel cell electric trains. And that bottom picture there shows the Breeze, which is been developed for the UK market by Alstom, which is a hydrogen fuel cell electric train designed to replace diesel units on sort of more urban train lines. Sorry, the photograph at the top is the Breeze. The photograph at the bottom is the Hydroflex, which is on trial in the UK. Heavy duty and off-road, so trucks and off-road vehicles are a really interesting application area for hydrogen fuel cell electric powertrains, again, because their energy requirements are such that it's quite hard to envisage technical solutions which will deliver that using batteries alone. That's the picture there of JCB, who are very active in this space. It's interesting to see Bosch's announcements around hydrogen fuel cell powertrains, again, focusing initially on trucks, and certainly in all of the conversations I'm having with folk, these kind of heavy duty vehicles are where a lot of the interest sits at the moment. And then I should say that all of those fuel cells use a polymer fuel cell, which is a lowish temperature fuel cell, runs about 100 degrees centigrade, uses platinum group metal catalysts. Johnson Matthey are very active in that space as well. But just to say, we do have a UK company called Ceres Power, which I'm declaring interest as one of the founders, producing a higher temperature fuel cell. It's a metal supported a solid oxide fuel cell, as it would be known, and that's being put into buses in China. These are not hydrogen buses. These are actually buses running on fossil fuels, but this type of fuel cell will run very well on those, but they also run very well on hydrogen. So this is another type of technology that is useful for some types of transport applications, including ships and trains and so on as well. So I'll park it there. That's my quick whiz through my opening comments, and we have some website links there, or you can email me if you want links to any of the information I've provided. So thank you very much.
Okay, thank you very much. Very pleased to be here, and some great speakers so far. So I hope I can keep up to standard. I'll talk a little bit about hydrogen in automotive. Obviously, my position at the moment is with Jaguar Land Rover, and we had a bit of an unveil recently with Thierry Bolloré, our new CEO, announcing the Reimagine strategy, and that had an element of hydrogen in it. So the kind of the covers are off a little bit. Now we can talk about hydrogen and the fact that we're working on it. But what I'd like to do is just go over a couple of things that have been already mentioned, of course, the bigger picture of where hydrogen fits in the economy and what's driving my thinking behind why it will be interesting for automotive. And then really, asking the question, why again? It's why is it interesting for automotive? What does it give automotive, and why should we not just do everything with batteries? So with that in mind, can I have the next slide, please? Okay, so this is a fairly well understood picture now. All of the other speakers have mentioned the ecosystem behind hydrogen and how the electricity grid and the hydrogen production and storage can work together for a variety of different end uses. I just wanted to bring some numbers to this actually as well. So, we at the moment in the world, we make and use about 65-70 million tons of hydrogen annually, and that's predominantly from non-renewable sources, so coal and gas. One of the first things we really need to think about is decarbonising that. And to put that in perspective, in automotive terms, 65 million tons of hydrogen is enough to power the 1.4 billion vehicles on the road in the world at the moment. It's enough to power those for 5,000 kilometers each per year if they were run as fuel cell vehicles. So it's a significant amount of hydrogen that is made and used in the world so far. It's not a new concept to make it, transport it, and use it safely. So that's really the first point I want to make. The decarbonising heating piece, that's been well covered so far. I just wanted to also bring a couple of numbers to the costs associated with electrifying heating in homes. So it seems like a good idea. Take out your gas boilers, put in heat pumps, etc. So about 12% of the UK housing stock is social housing. Various county councils have looked at the costs associated with moving their housing stock to Future Home Standard, which is a path to net zero. It's not net zero. And the cost of that is about £100 billion. Then if we move into the private sector, homes that are built now to current building regs, if to move those to Future Home Standard, which is coming in 5 years, is about a £20,000 ask. Now, a lot of the older housing stock, so we still have 70-odd% of the older housing stock in the UK, to electrify the heating and the cooking, etc., in those houses, but heating particularly, doesn't make sense until you've insulated it properly and you've made it more energy efficient. There's a project in Nottingham called Energy Sprong, which looked at the costs of doing this on pre-war housing stock, pre-1914 housing stock. They had a target of £60,000 per house, but they didn't manage to achieve it. So the costs to the end user of electrification of home heating and home cooking is really has to be considered in the mix here. But as all the other speakers have said, it will be a blend. Future homes, yes, certainly electrification is a viable way forward, but retrofitting, we really have to consider where we're going to get the money from to do that. I won't go into the energy system smoothing again, because that's been well covered, or the decarbonisation of steel making processes, things like that. But then my speciality is the transport applications. So transport applications where you just need a lot of energy on board really do benefit from the application of hydrogen. And this means heavy vehicles that tow, heavy duty vehicles that need large load capacity, vehicles that need to refill quickly because they are on quick turnaround duty cycles, and also vehicles that operate in low temperature conditions where you need a lot of energy for maintaining cabin comfort. So there are a lot of reasons why you might use hydrogen in the heavier transport application. So if I could have the next slide, please. So the one that we're really about, JLR, is customer experience. Now, what does our customer experience, and is that experience good? The upside to hydrogen with in automotive, in passenger cars, is the convenience of a quick fill. And then once you get into longer journeys, so just to explain the chart on the right there, the light green bits are traveling time and the dark green bits are stopping time. And if you take a notional longer journey, 800 kilometers, you come to the conclusion that a battery car with a decent range in good conditions, i.e. 25 degrees Celsius, it takes about an hour and a half longer to do 800 kilometers than it does to do it in a fuel cell or a combustion engine car. And that's true whether you are driving a passenger car or a heavy duty vehicle. You know, it's about the average speed you can actually maintain on those long journeys. Okay, if I could have the next slide, please. But there aren't any hydrogen filling stations around anywhere. That's the criticism. No hydrogen stations around. Well, yes and no. I mean, there are places in the world that are really going, headfirst into hydrogen economy, and Japan really has been the leading light there. And the commitment to hydrogen stations has ramped up in recent years, and my view is that it will continue to exceed the stated objectives already in the places that are interested in hydrogen economies. In Europe, I think Germany is probably the highlight as the leader there, with over 90 filling stations at the moment. And the question really comes down to how many filling stations is enough? Where do we need to get to? I have, within 2 miles of my home in Nottingham, I have 19 petrol stations. That's clearly too many. So the rule of thumb that I work to, and a lot of others work to, is about 1 in 20 fueling stations should be hydrogen capable to provide a good coverage nationally. And in the UK, there are about 8,000 filling stations, petrol, diesel. So that means if we could get to about 400, we would have a very substantial network. Okay, if I could have the next slide, please. So coming back to why are automotive interested in hydrogen? Why not just do it all with batteries? The mass of the power pack, and I'll explain that in a second, is significantly lighter when you need a lot of onboard energy. It's significantly lighter for fuel cells and hydrogen when you need a lot of onboard energy. What I did in this slide, a little bit busy, apologies for that, is I made a calculation of the onboard energy available from either a battery power pack, so that is just the battery on a BEV, or a fuel cell power pack, and that means the fuel cell system, so the fuel cell engine, the DC converter, a hybrid battery to give the same power as the BEV battery, and the hydrogen tanks. And you can see, of course, what happens is the relationship between energy and mass with batteries is linear, and that's shown in blue for 2021 and projected out to 2030. So if you increase the amount of energy you need for, or you want on your vehicle for propulsion, then you need to increase the mass of the batteries. With fuel cells, of course, you start with the fuel cell engine, the mass of that initially, with zero hydrogen on board or zero tanks. And of course, you have no energy on board for propulsion, but you have some mass associated with the engine. And then you increase the energy available for propulsion by adding fuel tanks, so hydrogen tanks, really. And you can see, obviously, there's a crossover in 2021 at 55 kilowatt hours, thereabouts. The fuel cell power pack becomes a lighter weight option than the battery power pack, so the battery unit. projecting out to 2030, that goes in favor of battery somewhat, in that the crossover point becomes around 85 kilowatt hours. So there's a lot of debate in the industry at the moment about exactly how much energy we do need on board. And you can see those grey lines lurking in the back there. What I've done there is I've scaled the available energy on board for a battery vehicle at -7 degrees. So at -7 degrees, if you go to Argonne National Laboratory website, you can get some really good data on the range loss at low temperature for a number of battery vehicles, and it comes down to about 40% compared to 25 degrees C and -7 degrees C. So you can see there that even in 2030, fuel cell and hydrogen has a significant mass advantage on board. Okay, if I could have the next slide, please. The other key challenge for automotive, of course, is the battery material supply constraints. The challenge of decarbonizing transport is absolutely massive. The takeaway from this slide should be that the ramp up needed in battery supply just to deliver on transport decarbonization is absolutely huge. There will be a lot of stress on supply chain there. Decarbonizing transport with batteries alone, I think, is a huge risk. We will need not just fuel cells and hydrogen, but we will need synthetic fuels, whose feedstock, by the way, is hydrogen, to deliver on the decarbonization challenge. Okay, if we can have the next slide, please. So the controversial question I will leave you with is, are we in or out? Really, I've spent a lot of time in China and Japan over the last 7 or 8 years, and I see a very bullish approach there. And the map, this is a very good slide from FTI Consulting. Thank you for the use of that. And the question really is, do we want to be a part of the hydrogen rollout and the hydrogen economies that are emerging around the world, or don't we? It's a very simple question. So, and I hope the hydrogen plan strategy will bring some answers to that. Thank you very much.
So I'd like to invite my other speakers back to the session, and we're going to see if we can take a few of the questions live. I think we're starting first of all with a question from, I think it's Paul Turner. Hi, Paul.
Hi, hope you can all hear me.
Yes, we can.
Yep.
Okay, thank you. Why does the panel believe we will not use hydrogen in ICEs, as the efficiency at load is similar to fuel cells, and the ICE can easily be made zero emissions? This is just about design, not science. And I'd like to add on, best must not be the enemy of better.
Yeah, great question. I mean, the efficiency at high load, yeah, there is some public information, very good, once again, Argonne National Laboratory, very good analysis of the Mirai efficiency. Peak efficiency there is about 63% a system level, and then goes down to about 42% at full load. So I would say that fuel cells are probably more efficient through the entire load range than ICEs. And onboard vehicles, packaging is absolutely the challenge. Getting enough hydrogen on board to to give that to actually enable the advantages of hydrogen. So that's long range and good range once you've refilled. It means that you need to get as much hydrogen on board as possible, really, and you need to use that hydrogen as efficiently as possible. And so while, yes, at full load, the ICE and the fuel cell can be similar efficiencies, actually at part load, city driving, over EPA type cycles, the fuel cell is about 50% better. And that means you need less hydrogen on board, and it reduces the packaging challenge and the cost challenge. but in somewhere where you've got more space, heavy duty vehicles, for example, yes, no problem.
I'd just like to sort of make a point that also the cost advantage of an ICE is much lower, allowing good design to take place to give you the packaging space. But our view is that the ICE may be very useful for heavy goods vehicles going through to heavy transport and to marine shipping.
And just to, I think, prop up your case, Paul, you know, cooking hydrogen really can be used in ICEs, whereas it needs a lot of purification for fuel cells. So, you know, I think there probably is a place for it. It's just the packaging challenge we have on board vehicles, which is getting more severe as we move to dedicated battery platforms that we're pivoting off. You know, it really puts a lot of, no pun intended, pressure on the hydrogen systems.
Ralph, can I just add, I think there's also the NOx emission issue that you just need to pay attention to with a hydrogen combustion. That's not to say it can't be managed, but the high flame temperature gives you more concerns over NOx. Yeah,
we're running engines today with virtually zero NOx, lower than we can measure.
Next, we've got a question, unfortunately not live, but and again, this sparked a little bit of weight, and we see this in the media from an attendee called John Tung. There are some high-profile individuals who are very negative about hydrogen as a practical solution for passenger vehicles, most recognised being Elon Musk, describing it as a fuel cell. How would you respond to this, and why should it be considered for this purpose? So I'm not sure if there are any critics out there who wants to come back on that one.
Elon Musk has a mission, and he's very good at it. I think, as Ralph has explained terribly well, right? It comes down to the functional requirements of the vehicle, and it's unhelpful to take that type of narrative. For vehicles, for transport applications, for vehicles which have a high energy requirement, then hydrogen, or indeed any other low carbon molecule, whether that's a synthetic fuel, right, an e-fuel, or ammonia for shipping applications, perhaps, these start to become attractive relative to battery electric as the energy requirements go up. Ralph articulated and showed that very well for the applications he was looking at. So from a kind of decarbonisation perspective, it's unhelpful to say that these things have no value, especially from the platform of his publicity. So I'm afraid in this case, I completely disagree with his comment. For light duty vehicles, you know, the opposite applies. And I think if you're going to drive to Tesco's in a small vehicle, do it on electricity. If you're going to drive a truck across North America, you probably want to do it on a low carbon molecule, like hydrogen.
Yeah, it's free headlines for Elon, isn't it? You know, every time he you know, he brings a culture war to bear, it's free headlines. So we seem to be, you know, living in a time of culture wars. Everything has to be against something else, and Elon's very good at making use of that. He is right in a sense that you know, the future passenger car market will be dominated by batteries. You know, I believe that, but a significant proportion of it will be, you know, low carbon molecules, as Nigel says. I happen to think that will be hydrogen and fuel cells, but it will be a significant proportion of it. And I think the big debate in the automotive industry at the moment is just where that crossover point is. Everyone understands it's to do with mass and range. It's just a question of where that crossover point is.
Thanks. I've got another question here from Ahmed Zaid. What are some of the main temperature management related challenges in the development of hydrogen-based vehicles, both from fuel cell based or otherwise? I don't know if either Sam or Nigel want to pick that up.
So we have what I call a top hose temperature of a combustion engine vehicle around 110, 115 Celsius these days. That's the temperature of the cooling fluid that goes into the radiator. And that gives you a delta temperature to your environment of let's say 70 degrees, if you're operating in a 40 degrees C environment. And that's the basis on which you can project temperature, thermodynamics and all that. Temperature flows or heat flows from hot to cold. So with a fuel cell, maximum top host temperature we're looking at these days is probably 80, 85 Celsius. And that gives you a 40 degrees C difference to your environment. And therefore your cooling capacity is halved. So the challenge, yes, is getting high performance radiators and getting the airflow through the vehicle to maintain the cooling of the fuel cell. And in fact, I think to answer the question, more directly, if every 2 or 3 degrees C improvement we can get in the core temperature of the fuel cell gives us a huge advantage on the vehicle packaging and ancillaries management, energy management side. So if we were able to push the operating temperature up to 90, 95 degrees C, I think that would be an enormous advantage.
Thanks, Ralph. I've got a question probably to Sam and Claire, really. I mean, we've seen, I think, from both your presentation, the timelines that, a lot of countries are almost ahead of the UK in their strategies and developments going forward. So would you say that even without a strategy, this means that we're a long way behind, or do you see us catching up, or are there areas in which we should prioritise or recognise that maybe we can't be competitive?
Do you want to go first, Claire, or shall I?
I wouldn't say that it's fair that we're behind. I think there are certainly countries that are moving very rapidly, and that the UK does risk getting left behind if we don't, start to move a little bit quicker over the next sort of 12 months or so. I think that the sort of business models work will be very much a sort of starting gun on sort of things actually starting to scale in the UK, and we're already starting to see some of those sort of key projects sort of receiving funding and starting to move forwards, and so I think we are going to see the UK really starting to ramp up over the next 2 or 3 years. So I think I wouldn't say that we are by any means behind, but I think that we very much need to, put the pedal to the floor, and we are in a race, and there are other countries that are taking this very, very seriously, and UK government really needs to get a wriggle on.
Sam, have you got anything to add?
Yeah, I clearly agree with Claire. I think what I would say is that some of this again is packaging. So to date, a lot of countries have announced large ambitions, large funding pools, but absolutely no detail or real credibility to them. So it's all right to announce a big number, but until you've got the structure and the actual building blocks, it doesn't really mean that much. One word of caution, though, is that does attract both press and investors. And so we will need to think about that. But in terms of actual real projects, we have some of the largest, most ambitious projects here in the UK that will be flagship projects globally. What we're not necessarily good at is pulling all of the different strands of effort together to make that one big number. So if we look at some of the the billions of pounds that are on offer from European countries, well, if we said that actually that was made up of the hydrogen supply competition that we've been just going through, the net zero hydrogen fund, the work in academia, such as Nigel's institutions, the business models that are to come, the carbon capture and storage work, the stuff in Department for Transport, and we pulled it all together, we'd end up with a much bigger number. We don't do that. We don't like these big, massive announcements. But for me, it's about the real detail that will be critical, and that will enable these projects to happen.
Nigel, I saw you came off mute. Did you have something you wanted to add?
I mean, yeah, I mean, just to reinforce that point, I think that that's both a perception issue, but it's also a reality issue. I mean, actually, you can't have there's no point. A lot of countries are focusing on making hydrogen. Well, there's no point making it if you can't transport, store it, and use it. So there's a co-creation across the whole supply chain that's needed, and that has to be in an integrated fashion. So actually, I mean, to pick up on Sam's point, the fact that we do these things separately is actually not only a kind of perception challenge, but it's actually there would be benefits to having a more integrated perspective, because hydrogen is simply an energy carrier, right? It's just a means of moving energy around, and so its role is to the system, and you have to have this kind of co-creation across the whole supply chain. And I think that would be something that would be there was opportunities to do that better. And indeed to join across the TRLs as well. So I represent the academic community here on the panel. And I think, having a stronger and tighter integration between the science base and the development and demonstration activities, both from a training of people perspective and indeed feeding back into future research challenges. We have some great technology companies in the UK and some great system integrators and a great science base. So, I mean, to pick up on Claire's point as well, we are well placed to be competitive here. In fact, probably better placed than we are in many other sectors. So it's a great place to be moving from, and we have to take full advantage of that. We're not behind, but there's lots of noise elsewhere, and we need to compete. Thank you.
So, Philippa, just to come back quickly, I think you've got a panel that's all agreeing, which is not always great, but no, I think what Nigel said is really important. We do have some really good companies in this space, but we will need to attract OEMs. We've got Jaguar Land Rover, but are we going to have the number of cars or vehicles coming into the country? If we don't, because another country's got a more attractive proposition, then that will push us behind, or at least limit the breadth of use cases for hydrogen. I can see some pragmatic take in government where they, particularly because of the way that the government's structured, the Department of Business, Energy and Industrial Strategy has started by focusing on industry. It's in their remit. We need that broad structure and management across multiple different departments, including the Department for Transport. We need a decision following what Ralph was says. What are we doing around heating? Heating's a massive emission source. At the moment, there are bits that are running at different speeds, and there are bits that are running in different departments. So some real joined up thinking on the part of government. I think industry, academia, everyone else is kind of raring to go and ready to go.
Yeah, sounds like that strategy can't come soon enough, really, to help develop that. Okay, we've run out of time, unfortunately. So thank you very much to my 4 speakers, to Ralph, to Sam, to Claire and to Nigel. Really appreciate you taking the time out today.